Hello, welcome to week 3. We'll be talking about brute force method this week. And to be honest, I'm not sure if I can fill up 2 hours worth of lectures just talking about brute force because, well, it's brute force. It's nothing complicated. Back in the first year, before you learn about efficient codes, before you learn how to code well, you probably did stuff using brute force. So this is something that you already know, hopefully. But if you look at what we've done so far, we pretty much repeat what you did in year 1 and year 2. I mean, we started talking about problems again, talking about algorithms. We talked about complexity, big O notation, which we've done in Com 2 to 5, Com 2010. We talked about correctness. We went a little bit deeper maybe with variance in induction, but you've seen the basic back in Com 2 to 5, Com 2010. Even back in Com 1 to 5, Com 1010, you already did a little bit of this. So yeah, I'm going to talk about brute force again, right? Just like a revision of what you've done in the first 2 years. And I still think it's a useful technique, being able to do something using brute force. Because if you're stuck, if you have to solve something quickly, and you don't know a good way to do it, then you can always start with brute force. And even when you brute force, I mean, the end solution might be bad, sure, but as you're doing it, as you're trying to solve the problem using brute force, it may give you ideas on how to write an efficient algorithm for it. All right, because the idea is like, you know how I was talking about problems being input and outputs. Like always look at the input, look at the input, look at the input. When you do brute force, you will try to go through every possible inputs, right, to find the answer, and this can lead you to a nice solution because you realize, oh, this input and that input, they're the same. Oh, I don't have to worry about this input. I don't have to worry about the input. So you find improvements in your code if you try. Well, I mean, you start using brute force and then you can find ways to improve it. And also, my feeling is that you didn't get that much practice in brute forcing because the way we teach computing, it seems that we go to efficient methods very quickly. Like even starting from Com 1010, we tell you how to do things efficiently very quickly. So there's not that much brute force, and a lot of brute forcing requires recursion. So we didn't spend much time on that either, like back in Com 1010, because recursion is already hard, even for simple stuff. And when we went to Com 2 to 5, Com 2010, we started doing efficient stuff. So we can't ignore brute force in a way, right? So it would be nice to just go back to it, formalize a few things, like explain what brute force does, and how you should do it, write some code, and yeah, that's what we're going to be doing this week. So what are we going to talk about? We're going to talk about search space. So what I mean by search space is you generate all possibilities, like all possible answers, you generate all of them, then how do you actually generate them and how do you go through them? That's the search space. So we have to talk about permutation and combinations. I'll do a review on that. And then we talk about recursive backtracking, which you have heard before, hopefully. I'm sure there are other subjects where you do recursive backtracking, maybe the AI subject. And then also a bit about branch and bound. I mean, these two are pretty similar, like they kind of overlap. So basically, how do you do brute force? But before talking about brute force methods, I want to talk a bit about tractable and intractable problems. We already talked about this in week 1, and we're going to talk about some more in week 12, week 13, when we talk about P versus NP. And it's kind of relevant this week, so maybe we can spend a bit of time on it. So, tractable problems are problems which are solvable in polynomial time. That means we have an algorithm which is big O n to the k, where k is some constant. And we call these algorithms the good algorithms. This is just how we see things, right? If an algorithm is polynomial, we say it's good. If an algorithm is exponential or worse, we say that's bad. The thing is, tractable problems are probably not as interesting because we consider them to be solved. I mean, if you want to go from intractable to tractable, that's kind of sexy. That's kind of great because you go from bad to good. You go from exponential to polynomial. But going from good to better is hard. and also people consider them to be solved. So if you come up with a better solution, so what? I mean, one example of this is in week 1 when we talk about finding the minimum and the maximum of an array. And I'll show you that I can do that in 3n over 2 as opposed to doing it in 2n, which is more obvious. So yeah, I thought that was cool, but you're only making like 25% improvement, which is at the end of the day not that much. I mean, nothing compared to going from 2 to the n to n to the 10, for example, like, going from exponential to polynomial. Intractable problems, on the other hand, they get a lot more attention. People do more research on these because I guess they're more interesting. These are problems where you don't know if you have any good polynomial time solution for it. So whatever we have is something worse than polynomial. And when I say not polynomial, when I say worse than polynomial, I don't always mean exponential, because you can be worse than exponential. You can go factorial, or you can go super exponential, something like 2 to the 2 to the n, right? That's just humongous. You can also have something between polynomial and exponential. So for example, n to the log n. So you cannot bound this above using n to the k, because obviously k is a constant and log n grows according to n. So n log n will eventually dominate n to the k, like for whatever constant. Even n to the log n will also do that. And these guys, they have different names. Well, people call them different names. Sometimes you hear quasi-polynomial, sometimes you hear super polynomial, sometimes you hear sub-exponential. Doesn't really matter what you call them, just be aware that they exist somewhere between polynomial and exponential. And if you have an algorithm, if you have a problem where the algorithm is in this kind of complexity, then you say they're intractable, right? And remember that the reason why we study intractable problems is not because we're trying to solve them in polynomial time. That's just too hard. We study them so that if we ever encounter them in real life, if we see these problems, we can see that they're hard, and we're not going to waste time trying to find a polynomial time algorithm for it. Now, there's also a different kind of intractable problems. Maybe something you haven't thought about before. So what if I give you a problem and the number of solution is exponential? For example, I give you a knapsack. I hope you know what knapsack is by now. So I give you a knapsack and I ask you, give me all the possible combinations where the total weight of the item is less than k. Right? There is an exponential combination of these. Or traveling salesman. So I'm not going to ask you to give me the cheapest route from A to B, but I'm asking you to give me all the routes from A to B that cost less than k. Again, there is an exponential combination of these, right? So if you have to give me an exponential number of solutions, then you will have to produce them using an exponential number of operations. So automatically they're intractable. Like this problem is automatically intractable, right? So yeah, that's a different kind of intractable problems, but this is something we're not going to worry about. Just know that they exist. And generally, when we talk about intractable problems, we're just going to talk about the stuff we talked about in the previous slide, right? So it's a problem, you're used to it. It has a solution which is simple, but it will cost us non-polynomial time to do it. Like it's going to cost us more expensive than polynomial time to get it. I also want to talk about intractable solution as opposed to intractable problems, because this is a term that I use from time to time. And I hear other people use it as well, so it's not just me, but I can't seem to find anything on Google about it. So let me just tell you what I mean. So when I say intractable solution, I mean this is an algorithm where the complexity is worse than polynomial time. So if I say tractable solution, that means this is an algorithm which is in polynomial time. So I make that distinction between intractable solution and intractable problem because you can have a problem which is tractable with an intractable solution. So what I mean there is you can have a problem which is easy, but you write a slow algorithm for it. For example, burger sort. So if you don't know what burger sort is, you sort an array by randomizing it. So imagine you have a deck of cards, you throw it up in the air, you pick up the cards one by one, and you hope that it's sorted. If you do this enough time, hopefully it will actually be sorted. And the complexity is n factorial because there's n factorial combinations. So, well, hopefully if you go through all the combinations, one of them is sorted. So obviously that is stupid, but it's a valid algorithm. It's just that the problem itself is tractable because sorting you can do n log n and employing more time. But we chose to do it using an intractable solution. So if you have a problem which is intractable and your solution is also intractable, that's fair enough. But if your problem is tractable and you chose to use an intractable solution to it, that's not good. So please don't do something like that. But anyway, I hope that's clear why I differentiate between intractable solution and intractable problems. Now, back to intractable problems. Just because a problem is hard, it doesn't mean that it's hard to come up with a solution for it. So, for example, if you had a tractable problem, then as we said before, you can probably come up with an intractable solution for it easily. Now, coming up with a tractable solution for a tractable problem can be difficult. Like you have a tractable problem, you want to work out what the efficient solution is, that can be hard. But if you just have a problem like tractable or intractable, if you just have a problem and you want to solve it, if you want to come up with a solution for it, this is not hard. You just brute force it. Just as a trivia, this is not always true because there are problems which you cannot solve. If you're interested in that, you can click on the link there on the Nature article. This is very theoretical. You have to go back to someone called Kurt Gödel. So this means that brute force is a good starting point when you're trying to solve algorithms. Well, maybe it's not the best one all the time. Well, I definitely don't think it's the best one all the time. But it's good because it's easy to write. And when you brute force, it lets you recognize the patterns in the solutions. Because if you have the brute force solutions, then you can easily generate different solutions for different inputs. And then when you look at the different solutions, maybe you can catch some patterns. Maybe you can discern like a way to do it better. Also, sometimes that is the only solution. And this is why we say that if your algorithm is exponential, then it's bad. Why? Because when you're brute forcing something, look, it's exponential, right? So if your algorithm is also exponential, are you actually doing that much better? Right? Okay, so that's that will be the end of this lecture, of this video. I'm kind of sorry that I feel like I'm saying a lot of things here and they're a bit disjointed from, but everything I said is related to the whole idea of like intractable problems and leading to why we want to use brute force to solve them. I mean, this is really the key slide here, saying that, well, we want to do brute force because it's easy and it can lead us to better solutions. And the rest are just giving you more background on intractability, which is going to come into play a bit later when we talk about B percent P. But yeah, I think that is enough for one video. We'll come back and we'll talk about search space in the next video. All right, I'll see you there.